Alright, now let's look at the multipath. So if you are going to receive, this is a transmitter, this is a receiver, and you will get many signals. Every building will be transmitting you some reflection of the signal, right? And they will all have different phases. So what you get is, you might send this, just one pulse in time domain. Now you have to remember where I am talking about. This is in time domain. I just sent you one square pulse. You will get 4 different square pulses. Actually, you might get n different pulses depending upon the number of the reflectors. So this came directly. This came from one reflection. This came from second reflection somewhere. This came from third reflection somewhere, and on and on. Okay. So every little point will be reflecting. So here is one way to think about this thing, that every building is a mirror, and you are sending a flashlight. You are just turning the flashlight. Some light goes to the mirror, and then mirror sends it that way, right? This is another building. This is another mirror. This is sending that way. There is another mirror. Everything is a mirror. If it was light, you will get lots of different rays. Here you will get lots of radio waves. So you send one and you get many. Yeah.
So the reflection is only happening with glasses?
Huh?
The reflection happens only with glasses?
Light is only, okay, so it depends upon the signal, right? Light reflects only with the glass. Radio waves can reflect with these things. Yeah, with everything. This table, that table, me, everybody is reflecting. Okay, so the thing is, I haven't talked about frequency yet. I'm just talking in the time domain. If you just send this pulse, which is just a very small impulse actually, right? In frequency domain, this will look very different. In frequency domain, it might be very wide in many frequencies. So I'm not going to take you there right now until I get there. So we'll talk about the frequency domain later. But in time domain, if you just send one pulse, you will get many pulses. So all the signals, whether it is radio wave or light or whatever, I mean, the same thing applies to fiber. You send them people inside. If they are like a tunnel. If you send things or people who are very tall and very thin, beautiful people, what comes out is people who are very short and very thick. So as the tunnel becomes larger and larger, they become smaller and smaller, of course, and they become thicker and thicker. So we all know about so basically if you send something, power, you send this, you send, let's say, a blue pulse and a red pulse in time domain. The blue pulse will come out as a very wide blue pulse. Actually, don't think about the color, it's just pulse number 1. Pulse number 2 will also become wider, and they will start colliding in each other. I mean, if people become too fat, they will not fit in the tunnel. Right? And so you will lose a lot of energy for nothing. Okay? So the decrease in the amplitude as you go down is called attenuation. The increase in the width as you go down is called dispersion. Okay, both things happen. Attenuation, we saw the formula. Dispersion is this width thing which we haven't really gave you the formula for yet. But I showed you the dispersion, that I sent one pulse this thin and it came out like this thick. You see? So this is all one pulse I sent, and now it is kind of occupying this whole time. Now if I was going to send 2 pulses in the beginning here, they will be just getting into each other. Right? Because they are both wider in time. This width in time is called dispersion. Yeah.
Could you go to the next slide, please? Why at the very bottom, on the bottom right, the power versus time, why is it consistent power over the width of that? Shouldn't it be attenuating, or is it...
Why power is less?
Yeah, why is the power consistent throughout the entire...
Oh, no. The thing is, this is simplification. This is simply, I mean, I don't want to go into, I mean, if I were to draw exact graph, I don't know what it will look like. It will be probably more complicated than this. I'm just trying to show that it is less, the height is less means the power level is less, and we already know that every d squared will come down, right? I mean it will come down as a function of d squared, so it is less, and then we know the bits will be high. Now I just showed you square pulses doesn't mean that we will get square pulses. Actually that's another thing, that actually they may not be even be square pulses, there would be multiple pulses like this spread over all over. So in fact, I mean like this cartoon continues later on. If when I teach optical networking, which I do sometimes, then we use the same cartoon, and then there's some other phenomena. You send 2 and 3 people come out if the tunnel is long enough. Alright? So there are all kinds of phenomena which are much easier to understand with the cartoon than with all the formulas that I give you. So multipath propagation is basically you send 2 pulses and you get lots of pulses. Okay, this one has 4 resulted in 4 pulses. Now this is not a square wave, right? Like you asked the question, right, Steve? So this one is not a square wave either, but now they're running into each other.
If, like, let's say the last multipath pulse interferes with the first multipath pulse of the second signal, then would that interference like cause a lot of like loss of data?
Yeah, right. So that's what basically it is. So what happens is, if you know that in your medium this pulse can go this much distance, then you will keep the second pulse that much away. And that means you cannot send that many bits per second. This is second. You cannot send that many. If we call this a symbol, then we cannot send that many symbols per second or bits per second. So you are limited, because multipath limits the number of bits per second you can send. And so this is called delay spread. Delay spread is the time between the first and the last version of the signal. And actually we don't take absolute last version, which may come like million days later. We take up to certain power. Let's say I send 1 watt, or I send 1 dB, and if I get something up to 1/10 dB, that's all I care about, and anything less than that I forget. Yeah.
So it's not only advantages of directional signals, that there's less
reflection. Well, that would be one possibility. Yeah, and the thing is, so there is a positive and negative for everything. So now you brought up this question, which I was not going to get into, but you see, if I just speak directional, then if suppose I happen to pick the wrong direction, then they cannot get it, right? So that is called deafness. And I mean, so there are all kinds of phenomena. Alright, delay spread. So delay spread is what I wanted to introduce here. Delay spread means the signal becomes wider, and that is between the first and the last version of the signal. Fading is the fluctuation in the amplitude. Now the amplitude is not constant, right? And the delay fluctuation in the delay amplitude or phase or delay. That is called fading. And multipath may add constructively or destructively, so that is called fast fading. Basically, depending upon the phases, the signals may add, the signals may cancel each other out. So this is a little bit complicated, and I will show you a little bit of it. You don't really need to do all that math, because this thing is, if you pick up a book on wireless communication, and I have dozens of them, they are full of math. Okay, and that's a very important field, but we in this course are going to concentrate on the higher layers, and we just need to be able to talk to these people. So when they say there is a phase, there is a delay spread, you need to know that, because otherwise you can't write a paper on wireless. Okay? And so using a 2-ray model. Now, it turns out that so far we have been talking about d square everywhere. So we have been saying that the power goes down by a function of d as a square of this distance. Actually, it goes down as a power of d. Most likely, it is different actually in different places. If you go and measure it, it might be 2, it might be 3 over there, might be 4 over there, might be 5 over there. So depending upon the location or the media or actually everything else, it could be any power of d. Most likely, most common value is 4. Okay, so that is called d raised to minus 4 power law. And if you just do a 2-ray model, so people again, in wireless communication, people have shown that if you had a very simple thing, a transmitter here and a receiver there, then if they got 2 signals, one directly and one through reflection, if you add up, these two, you will get, this is a two-ray model, you will get formula which is received is transmitted times GT times GR times HT times HR, height of the transmitter times the height of the receiver divided by D square whole squared. So D raised to 4. And now you notice another term here, height. And so the higher you are, the more you receive, the higher you are, more you transmit. Because there is no transmission downward, everything that goes down is lost. Right? So that's why they put all these antennas on the top of the mountain, on the top of the big buildings, on the top of the long hotels, high hotel buildings.
Is it because the lambda is somehow, like dependent on the height of the antenna?
Right. So no, hold on. The question is the lambda in here? Yes, lambda is in here somewhere, and that probably is gotten into GTGR. And so your question is, if I have a different lambda, would the height? Okay, so this formula applies to all lambdas here. Now let's see. Now the lambda is coming up in this next picture here, and that is that this formula is valid for distances larger than this value. So it is not valid formula if the transmitter and receiver are very close. Okay? If they are far away, and how far away? Farther than this, 4 HT 4 bar upon lambda. Before that, actually, the previous formula was applying, which we had before, where we had clearly the lambda, but after a certain distance, this formula applies. I don't know whether to answer your question, but basically, so this is how it is related to lambda, is that for shorter distances, the original formula applied, for longer distances, this one applies, and the distance break is dependent upon the lambda.
So it's not an approximation, yes? So it's total.
So longer the lambda, the longer the height, higher the height you need for that D break. Note that the received power becomes independent of the frequency. So it becomes independent of lambda after that distance. Measured results show that n is anywhere from 1.5 to 5.5, typically 4. It turns out that sometimes if you move the receiver slightly, few centimeters, the signal may be very different than if it was few centimeters on the other side. That is called small scale fading. So the signal can vary basically, and by moving a little bit, you may get more power than less power and all that. So that is called small scale fading, and sometimes the small scale can add up to become bigger scale, or the small scale can cancel out totally, depending upon the phases again, right? If they're out of phase, they cancel out. If they're in phase, they add up. All right, so shadowing. Yeah, go ahead.
Sorry, on 2 slides back, what was N?
Where? In this one?
The one previous, the very bottom.
Oh, this is the power of n. Okay, good question. So this formula is written here. If you were to write it, you will say, if you bring d to the top, it will be d raised to minus 4. Right? If you put there n, that would be the n, d raised to minus n, and n can be, for short distance it was 2, for longer distance it is 4. So the n is the power of d. So this is called d raised to minus 4 power law, is that this is most common value of power for d. So actually, so basically what it is saying is that the signal strength goes down as the 4th power of d. So if you go twice the distance from a cellular tower, you get 1/16th. So twice the distance, 2 raised to minus 4, 16th, 1/16th power signal. Now shadowing has to do with, if you have something in between, somewhere on the way, then it will cast a shadow. So if you are, let's say, just thinking about the light, you are flashing a light from here, and you are receiving it here. If something on the way, you will cast a shadow. The light goes around, and then you see a shadow of the building. Same thing, in the radio waves, you will see a shadow. And so what will happen is the received power as you move would be like this, shadow. So if you were to plot the power as a function of log, so here power is in dB, so this is already log, and the distance is in log d, you would get a straight line. You know, basically if it was a fourth power log, this straight line will have a slope of 4. You know, I mean, maybe -4 or 1/4, something like that, right? So this will be a straight line, but it is actually not a straight power of 4, it is like this. The dotted line that you see, thin dotted line, that is the one we are talking about. That is how the power will look like if we were to measure the power, thin dotted line. So first thing you can do is you can ignore the small scale fading, and you get this thick dotted line fading, and then if you ignore the fading, then you get a very thick straight line. What is K? K dB. Basically PR upon PT is the ratio, right? PR upon PT, and so this is the attenuation, and so I mean K is basically the attenuation in dB. So by putting the word dB, we are making sure that you understand this is a log scale, not a linear scale, and K is just PR upon PT, and it starts from value K and goes down to value 0. So this is let's see, it clearly says here, this is shadowing and path loss. This is the little thin dotted line is multipath shadowing and path loss, and this is the path loss alone. Path loss, then we add the shadowing, and then we add multipath.